Hi everyone, it's Judy Warner. Welcome back to the OnTrack podcast. Today we talk to an engineer who is the senior staff signal integrity engineer for Amphenol, who makes connectors, especially for high-speed applications. He's going to talk to you about things you can implement right away, like right after this podcast, that is going to save you so much time and effort. So I think you're really going to enjoy this podcast. I'll also share some resources because Jason Ellison, our guest, actually writes articles for Altium relative to the subjects we're going to talk about today. So lean in and enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, hi, Jason. Thanks so much for joining us today on the OnTrack podcast. We're delighted to have you today.
Thanks. It's great to be here.
Well, Jason, before we get started, why don't you give us a brief introduction of who you are, who you work for, and a little bit of a thumbnail of your background in the industry.
Okay, so I'm Jason Ellison, and I am a signal integrity engineer working for Amphenol. Let's see, I graduated from Penn State with a Master's of Science in Engineering, and I've been in the signal integrity field for about 13 years. It started as an internship for Tyco Electronics, where they said, hey, you can work for Dennis Dupler making cable assemblies. I said, sure, I could solder some wires onto some printed circuit boards. That sounds easy. And ever since then, I've been fascinated with signal integrity and have jumped around from within a couple different companies, and now I'm at Amphenol.
So what kind of things do you do for Amphenol relative to signal integrity?
So I do some research and development. I currently study some de-embedding techniques, and I have a project that I am the signal integrity architect for, which is the XMX2 backplane and direct mate orthogonal system.
That's a mouthful. You said it like so easily. I think I would have trouble repeating that. So why don't you tell us a little bit about, since you're involved in, both connectors, backplane, board design, and how signal integrity, sort of plays across these different connections and platforms. What are some of the demands that sort of drive connector technology relative to high speed?
So the first thing that connectors need to do is form, fit, and function. So they need to be a certain shape, and typically that's some kind of rectangle, and it has to have hard metrics so that the chassis lines up correctly. Fit is usually with the height of the connector. So these things go into racks, and the racks have standard units like one RU, one rack unit. So the connector has to be only so high. And the function is where the signal integrity comes in. So that would be low reflections, low crosstalk. Can you route the thing on a printed circuit board? Can you attach it to the printed circuit board somehow? Make sure it doesn't fall off. Make sure that when the operator puts the blade into the rack, that the connector doesn't pop off and stuff like that. And of course, there's price. So in everything, no one wants to pay for a connector. A connector is literally just an object on the board that is a nuisance because it represents some dollar signs that no one really wants to put there. So we have to try to make it as cheap as possible.
Yeah, so do everything and make it free, basically.
Yep. Everyone would want it free if possible.
I know. It's sort of the unappreciated workhorse, isn't it? So in regards to signal integrity, I imagine the connectors have their own issues, like you were mentioning before, with reflection and insertion loss and those different things. How does that, since our audience is, usually EEs like yourself that spend a significant amount of their time designing on the board level, among other things, how does that sort of, flow down on the board level? What kind of demands does that place on the board level?
So the connector typically has, it's considered a discontinuity. And when I say a discontinuity, I mean that it's a reflection point. And if you look in the 10 gig days, a connector was just basically a lumped element that was a capacitive discontinuity. And that's typically because you had to have a via to put the connector onto, or you had a very large solder pad that the connector mounted to the board with. So anymore, the challenge is different. The connector usually has the printed circuit board in mind when it's designed. So things like discontinuities from the connector are built in or they're already considered when it's designed nowadays. And what becomes more of a challenge is the manufacturing of the printed circuit board. So what's happening in the 56 to 112G connector space is the vias to attach the printed circuit board are rather small. And so manufacturers have something called an aspect ratio. And typically, what an aspect ratio is a drill, like how big can your board be for a given drill size? So that would be, say your drill, for ease of calculation in our head, was 1 millimeter in diameter. So your board can, if it was a 12-to-1 aspect ratio, your board can be a maximum thickness of 12 millimeters. So that starts to become an issue when you talk about like 10 mil drills that have to go on back planes that are 8 millimeters thick. And now all of a sudden you have to play games. You have to drill from both sides. You have to go to board houses that have advanced technologies to get there. And they somehow have to plate these things all the way through with a really small drill. So those are the new challenges, in addition to just true position of the drill. So when the drill hit, like for a contemporary signal, say on the standard XMX platform, the drill hole size is 0.45 millimeters, and we want to have as small of a landing pad for that as possible. So if you want to have you need a pad to plate it, and you can't have that drill exceed the pad. So you need to have these drills going all the way through an 8 millimeter board, very straight, and so that the whole thing gets plated properly, and it becomes a tolerance challenge for the printed circuit board shops. And it only gets harder as the connectors get faster, because these drill hole size need to get smaller in order to enable the 112G transmission. The good news is it seems like there are plenty of board houses that can handle it. It's just you're gonna have to push them, and they're gonna cry about it when you tell them, like, yeah, I need a plus 8 mil annular ring on this one. They're like, oh god, that sounds horrible. And you're like, well, try your best and do what you have to do to make it work. And and they get better, and it works. I haven't really had any problems lately, so yeah.
It warms my heart to hear you talking about manufacturing and thinking about manufacturing in the context of your design. I think that so many designers today just don't have the opportunity to really be aware of what that means. And drilling, just true position and all of that isn't always, especially when it's on a big footprint of a big backplane. It's not always as easy as it would seem when we can do such really fine feature things these days. That aspect ratio can really throw you. So how did you come to learn so much about, what was required on the manufacturing side?
By making mistakes.
The School of Hard Knocks. I've gone to that one too.
Oh yeah, things look really nice and big on the screen, and then you tell the printed circuit board house, I need you to do this, and they say, I can't. And then you get into this back and forth of why not. And so what as a junior engineer, and I think this goes for everybody. Every junior engineer comes in and they say, "Oh, I'm just going to make it work. No, nothing's going to stop me." And you go in and you put these absurd requirements in on the board, and a lot of times you put these things in because of trends. So you'll work with lab technicians and folks that have a lot of really nice hands-on experience, and they'll tell you, "Oh, you just need a smaller drill." And you're like, "Okay, well, I'm going to use the smallest drill I could possibly use." And you use that, you think about that in a vacuum, and you don't bother and do all the other analysis that you need to make sure that a small drill really is the solution to your problem. You go to the printed circuit board house, and it comes back and it looks terrible. And then you ask the question, what happened? And then you do this a couple times, and then they tell, eventually you talk to somebody that gives you a good resource, which would be like IPC, I think it's 6012 or 612D or something like that. It's the
6012, I think.
It's the one that everyone references for their class, like class 2, class 3. Yeah. And so then you go into these documents and you just read the documents. You say, okay, well, now I know what these printed circuit board houses are requiring of my board. And the next step would be just march yourself into a printed circuit board house and say, well, this is what I'm trying to do. And then you get a tour. They show you all the challenges. And ultimately, what you learn from all of this is that you need to let the printed circuit board house tell you what you need to do to make your board work instead of the opposite. You
are my new best friend, Jason. We didn't even talk about this on our prep call, but boy.
Because here's the bottom line. If you don't have a solid, if you don't have a part that can be made over and over and over again, and you don't have a part that's mechanically solid, you could forget about the signal integrity. It doesn't even matter, because sure, anyone can make anything once. That's really easy. I've seen a guy with a glue gun and a file make something look really good signal integrity wise, but ask him to do it twice and it'll never happen. And that's how it is with printed circuit boards. You need to know what these board houses can do. You need to talk to them on the front end, tell them, do your best and tell them the justification of why you're doing what you're doing. And a lot of times you'll find they have really good insight on what to do. Mm-hmm. For example, I told a TTM recently that I needed a via to be centered in a constellation of vias. And really, the constellation didn't matter. It was how well that center one was in the center. And they said, well, that's good for you to tell me, because now what I would like you to do is put a note on the fab drawing that indicates that you're concerned about that, and the operator of the drill will then make sure that via is centered, because we could monitor one drill. We don't necessarily want to monitor all of the drills, but if you tell us I need to monitor several drills, it can work. So I guess it's experience. There's no books, unfortunately, that teach you these things. And the books,
nope.
The books are really good. The books that you'll find, the best ones, will talk about how things are manufactured. They'll talk about anodes and cathodes of plating, and they'll talk about the different kind of plating baths and why things are rough and why things are smooth and the chemicals used. And that's all well and good, but when it comes to actually making the thing work, a lot of times I haven't found a document or really just one book, like one text, that'll give you all this information. It's still somewhat cardinal knowledge.
Well, and the minute the ink dried, it'd be out of date.
That's true.
Right? Because it's always changing, and new things like laser drilling or the next thing comes out, right? And then all the parameters change. Have you ever taken a look at the PCB handbook, I think it's called, PCB handbook by Clyde Combs? I'll put that in the show notes. I don't know if you've seen it. It's a big fat book, but it's as close as you can get, I think, to what you're talking about being in a textbook. And each chapter is written by an expert of manufacturing or design. So it's real world. Yeah, and it's basically all these people, basically. It's Happy Holden and Clyde Combs. I think they've been printing it for now 60 years, but Clyde Combs is retired now. So the last edition came out, a year or two ago, and it was the last one, unless Happy Holden takes on the mantle, who's also been retired for 5 years. So, anyways, it's the closest thing that I've seen coming to that, and I will put it in the show notes so you guys can take a look at it. I think they sell it on Amazon. So, because of you being a master's in electrical engineering as well as the School of Hard Knocks, what are some things that you see that are done over and over again? For our audience, Jason does some writing for us, which is actually how we got acquainted, and writing about signal integrity, and I'll share stuff below. But, of those articles you've written, which ones or what are the issues that you see come up time and time again, that you wish you could communicate to your peers, that may be listening to this podcast, like, please do this thing. It'll save you time and money and effort.
Yeah. So I guess I have a couple. If we start at a signal integrity level, I think one of the biggest things that helped me, and it was really like serendipitous, because I did this mostly because I was writing these articles, is I found that there are equations that govern differential transmission line or strip lines, differential strip lines and single-ended strip lines that are analytical and no one's using. And so they've been made in the 70s, and I believe it's what has been implemented in CST's macros and ADS's blocks. So I looked up these papers, and I implemented the equations to calculate the differential impedance, and I was like, oh, well, that's great. I got a number. And then I started to use it. And every time I plugged in these numbers and I put it into CST, my answer was exactly right every time. And I was like, wow, that saved me so much time. And the reason, or what I'm going to compare it to, is my coworkers who don't typically use these equations. A lot of them, they like to... They think too much that the mesh of the CST or HFSS is going to dominate, and they're not going to get the right answer, or they're going to get an answer, and they're like, well, it just depends on the mesh of the machine. It doesn't matter what I really put in. I'll always get it close, but I'll never get it right on. Well, it's just not true. If you use the guidance of the equation, I found that every time it's correct. It's not even a question. It's every single time it's correct. And so I have that in the impedance, the differential impedance made easy blog, where I have a table, and I use the most common scenario where trace width and spacing are equal, and there's a ratio between your ground separation and the width of your traces. And if you just apply that ratio, you can either design your stack with your trace width in mind, or vice versa. You can go either way, and you will get it right on the first time, every time. It's fantastic, and that's the only way I do it anymore. I don't bother.
That's wild.
Yeah, it saves me so much time. Like, I literally, my coworkers, they'll solve footprints in CST 3-4 times trying to get a trace to be the right impedance, and here I am. I'm just like, yeah, I just dump it in and I'm good, And it's it's so much better. Another thing that I constantly fight, and it's really something that signal integrity engineers, I believe, need to start to track a little more, is the idea that reflections are the biggest problem now at 112 gig. So where things used to be is, like, say 25 gig, it was a combination of reflections and crosstalk. And typically the way you would get around your signal to noise ratio is you just drive down the crosstalk, because crosstalk was very significant at that point. So if you could squeeze out a couple dB of crosstalk, you'd get your eye open enough that it would work, and everything was great. And then you go to 56 gig PAM4, and it was kind of the same scenario. Customers said, well, we have 6 dB less signal noise ratio, so I need 6 dB less crosstalk, or it might have been 9. But anyway, whatever that number was, they said, drop your crosstalk by that amount. And all the connector companies said, yes, we could do that. And it was feasible at the time. But now with connectors need to be dense because chips are getting more dense, and if unless for the viewers, one of the ways that density is being increased is simply by doubling the amount of transmission lines on a chip. The SerDes used to have 128 differential pairs, and now they're moving to 256. Well, that means the connector has to be twice as dense. You can't, and one of the ways to decrease crosstalk is to lower density. Well, that's not an option. So we're coming right up against where crosstalk, you just cannot get it lower. But there's good news. You don't need it lower. I was at DesignCon this year, and I saw at least 3 connector systems that had adequately low crosstalk for 112 gig. Now, what that means is there's still systems that are struggling to bring up, and the reason is the reflection. So if you look at the contribution of noise in a 112 gig system today, typically it's like 1 to 5% is crosstalk, and on a poorly designed channel it'll be like 50% is reflections, and the whatever's left is the chip. And even in some cases you could have those reflections be as high as 80% if you're not if you're not monitoring your vias, because there's sometimes you have these vias in the link, and you're for whatever reason you have to transition to layers, and you will run into big problems. So I would tell signal integrity engineers, monitor your crosstalk or monitor your reflections. Your reflections are really where you will get the most amount of added signal to your system for the least amount of money. And literally all it is just you follow a couple of rules. You just make sure that your reflections are low from vias, transitions, and you use the correct connector system, and you make sure your chassis is built correctly, and you're going to be fine. 112 is actually quite achievable today, but reflections are going to be what all signal integrity engineers need to focus harder on now than crosstalk. That is the lowering the crosstalk is being the solution is usually a fallacy. The only time that it comes into play that you lower crosstalk and you get more bang for your buck is if you have connectors that are adjacent to chips. And it's a poor design practice, but unfortunately in some architectures it's necessary. So
well, that's fascinating. Yeah. I'm always interested as the speeds go up, how the problem used to be this and now it's this, Again, that's like I said, if we printed that book, at whatever speed, and now, it's already obsolete. It's kind of a myth buster. I like that one. Well, I'm gonna, like I said earlier, I'm gonna link to Jason's, both those articles that he mentioned, plus, I don't know, maybe you've written 8, 9 articles. I'm guessing somewhere around there. I looked at the page earlier today. But for our audience, I'm going to link to all of his articles, and then specifically to the 2 that he mentioned. So I hope that's 2 great takeaways for you. Jason, one last question for you. We used to do this thing, I haven't done it for a while, and I thought it'd be fun because you're a little bit younger than some of the savvy engineers that I know. When did you know, let me back up there. We call this Designers After Hours. So there's 2 things I want to ask you. When did you know you were going to be an engineer? And what is a hobby you have that we might be surprised to learn about you?
Yeah, so the engineering question, it's kind of silly, but this is the true story. I think it was 8th grade. In 8th grade, I was in homeroom, and a friend of mine, Eric Studley, and I were playing this thing called poppers. And it's where you take the foil from your gum, you wrap it around your thumb, and then you put it in your hand like this, and you go, and it pops up. And we were trying to shoot these things into the ceiling. And Eric was saying, "Hey man, you're good at math, right?" And I'm like, "Yeah, I'm all right." He goes, "You should be an electrical engineer. My brother's an electrical engineer, and he likes it. And all he said is he just needs to be good at math." And I'm like, All right, that sounds good. I'm gonna try that. That was really how it happened. And then I went to an open house at Penn State Wilkes-Barre, and there was this really cool guy, Dr. Fox, and he had us doing some P-Spice, and I liked it. And I did some circuits and physics, and I liked it, and it all kind of just like fell into place. But truly, the seed was that guy.
That's a great story. So, any fun or unusual hobbies that you have? Sometimes I notice that engineers have unique, sometimes artistic or creative outlets. Do you do anything? I know you have 2 small children, which I'm sure keeps you busy.
Yeah, that's actually where my hobby comes in. So my wife and I bought my son this like $30 Power Wheel from Target, and it was meant for 18 months old, and it had a little button on it on the handle to make it go. And developmentally, my kid at 18 months just could not push this button because like his just didn't have the thumb dexterity, and frankly the button was kind of hard to push for an 18-month-old. So the thing sat and it sat and it sat, and finally he's 3 years old and he pushes the button, and now we live on this big hill and the thing didn't move anywhere, and that just bothered me. So what I did was I somehow found another one, and I cannibalized the motor. So I took it from one motor to 2 motors. So it went from 1-wheel drive to 2-wheel drive. And then and I took it from a 6-volt system to a 20-volt system. And that thing just zoomed around the neighborhood like crazy. And my son was 5 years old, and he was still riding this thing until he destroyed the gearbox. He loved it. And so a friend of mine gave us legit Power Wheels from that their kids used to use on a farm. It's like a Kawasaki quad, and now I'm in the middle of souping that up for my son. We're putting headlights on it. I bought a 3D printer. I'm redoing the gearbox on it. I'm changing motors out, and so right now that's my hobby that I do outside, like my engineering type hobby is to soup up my son and daughter's Power Wheels. And my goal right now with this Kawasaki Ninja, I guess it's a Ninja, is to make it so that the left and the right wheels operate independently, so my son and daughter can do 0-degree turns with this thing. And I'm trying to make it so that there's a electric governor on it where I can try to like limit the amount of power that my son and daughter can put on the wheels initially until they get used to it, and then I want it to be like a 40-volt system, and then they could be zooming around the neighborhood and racing the other kids and everything. And because my son likes to go fast, I don't know that my daughter likes to go fast. She might just need something tuned up so she can get up the hill reliably, but my son definitely wants to go fast.
I hate to tell you, give you the diagnosis, Jason, but you're absolutely an engineer. If this wasn't obvious to you before, let me be the first to tell you, you've got the knack. Well, those are really fun stories. Thanks so much for sharing them, and thanks for dialing in today and giving some tips to our audience. I'll be sure to share your articles and keep writing, because it's been really well received what you're writing, and I know that our readers are really enjoying that. So thanks again for coming on today. For our listeners,
thank you.
Yeah, thank you, Jason.
Welcome. It was nice to talk
to our
to you.
listeners, thanks so much for joining us again. We hope you enjoyed this conversation with Jason Ellison. Please join us next time. Remember to like, subscribe, and send us your comments. And we will see you next time. Until then, remember to always stay on track.